Most people feel confident they understand gravity. Step onto a scale, read the number, and it seems obvious Earth pulls you downward. Drop an object and it falls. The moon stays with Earth, planets stay with the sun, and heavy things attract one another. For centuries, this picture has felt complete, but that sense of simplicity hides a deeper truth. Stand still for a moment and pay attention to what you actually feel. You're not sensing a pull downward. What you feel is the ground pressing upward against your feet. That upward pressure is the sensation of weight. The supposed downward pull itself is never felt directly. We only ever feel surfaces pushing back on us. That small observation leads to a much bigger question. If gravity is a pull, why do we never feel it acting on us? And why does the moon, which is constantly falling toward Earth, never actually get closer? It has been falling for billions of years, yet it simply keeps circling. That's not how ordinary pulling forces behave. For a long time, science accepted gravity as an invisible attraction acting instantly across empty space. Isaac Newton gave us equations that worked astonishingly well. They predicted motion with incredible accuracy, from falling apples to planetary paths. Yet even Newton admitted he didn't know how gravity operated. He could describe what it did, but not what it was. To see how this puzzle unfolded, we need to step back to the early days of astronomy. Before equations, there was observation. Tycho Brahe spent decades recording planetary positions with extraordinary care, measuring angles night after night. His data was far more precise than anyone else's, and that precision mattered. When Johannes Kepler analyzed those measurements, he tried fitting the planet's motions into perfect circles. The results were close, but not close enough. One planet, Mars, consistently missed the prediction by a small but undeniable amount. Kepler trusted the data more than the idea, so he abandoned circles entirely. After years of work, he found the answer: planets move in ellipses, with the sun slightly off-center. The math worked beautifully, but it raised a new mystery. Why should nature prefer ellipses at all? At the same time, Galileo was exploring motion closer to home. By rolling balls down inclined planes, he discovered something revolutionary: objects don't need constant pushing to keep moving. If friction were removed entirely, an object would continue forever in a straight line at constant speed. Motion itself required no explanation. Only changes in motion did. This idea, later called inertia, reshaped physics. Objects naturally move straight. If their path curves, something must be continually changing their direction. That insight unlocked Newton's breakthrough. Planets are not being carried along curved tracks. They are constantly trying to move straight. Their curved orbits mean something is deflecting them every moment. Newton called that deflection gravity, a universal attraction between masses, weakening with distance but acting everywhere. With that single idea, countless mysteries snapped into place. Planets follow elliptical paths because they are falling toward the sun while moving sideways. The moon orbits Earth for the same reason. Apples fall for the same reason. One rule governed both the heavens and the ground beneath our feet. For over 200 years, Newton's gravity explained nearly everything observed. It predicted tides, planetary wobbles, comets, eclipses, and even led to the discovery of unseen planets. But one strange fact remained unexplained. Drop a hammer and a feather in a vacuum, and they land together. The hammer has more mass, so gravity should pull it harder. But it also resists acceleration more strongly. Somehow, those two effects cancel perfectly. Every time, for every material ever tested, Newton's theory treated gravitational mass and inertial mass as separate concepts. Yet in reality, They are always exactly proportional. Why should that be true? Albert Einstein took that coincidence seriously. Instead of asking how gravity pulls, he asked what gravity actually is. Imagine being sealed inside a room. You feel weight pressing you to the floor. Are you standing on Earth? Or are you inside a rocket accelerating upward through empty space? No experiment inside the room can tell you which is which. Objects fall the same way. Scales read the same. Motion looks identical. This idea, called the equivalence principle, suggests something radical. Gravity and acceleration may not be different things at all. From this came a profound shift. Objects in free fall, apples, moons, satellites, astronauts, experience no force acting on them. They are not being pulled. They are moving naturally. What we call gravity appears only when something prevents that natural motion. Einstein's insight was that mass does not pull on mass. Instead, mass alters the structure of space and time themselves. Space and time form a single fabric, space-time, and massive objects bend that fabric. Objects then move along the straightest possible paths within that curved geometry. An apple falls not because Earth pulls it, but because space-time near Earth is curved and the straightest path leads inward. You standing on the ground are not at rest. You are being pushed away from that natural path by the floor beneath you. That upward push is what you feel as weight. This idea made a bold prediction: if space-time is curved, light should bend as well. During a solar eclipse, starlight passing near the sun was observed to shift position, exactly as Einstein predicted. Gravity affected light not through force, but through geometry. The same principle explains why astronauts float in orbit. Gravity there is nearly as strong as on Earth's surface. They feel weightless because they are falling freely along with their spacecraft, following spacetime's curves together. There is no push, no resistance, only natural motion. It also explains why Earth is round. Matter follows the geometry shaped by mass, settling into a form where all directions are equivalent. The shape emerges from the structure of spacetime itself. At extreme scales, this curvature becomes dramatic. Stars exist in balance between inward, curving spacetime and outward pressure from nuclear reactions. When that pressure fails, collapse follows. The result may be a neutron star, or, if mass is great enough, a black hole, where space-time curves so deeply that even light cannot escape. From planetary orbits to black holes, from falling apples to gravitational waves rippling across the universe, one idea connects them all: mass shapes space-time, and space-time guides motion. Newton gave us equations that work remarkably well and remain essential for everyday calculations. Einstein showed us what those equations were pointing toward all along. Gravity is not an invisible pull reaching across emptiness. It is the geometry of reality itself. When you step on a scale, you are not measuring how hard Earth pulls you down. You are measuring how hard the ground must push to keep you from falling freely through curved space-time. Once you see that, the universe looks different. Motion becomes natural. Falling becomes freedom. And gravity, no longer a mysterious force, becomes the quiet shape of the world we move through. Once gravity is understood as geometry rather than force, an important question naturally follows. Is this the final explanation? Einstein's theory of general relativity is astonishingly successful. It has passed every experimental test thrown at it for over a century. From GPS satellites adjusting for time distortion to black holes detected through gravitational waves, the predictions continue to match reality with breathtaking accuracy. And yet, despite its power, the theory is not complete. To see why, we need to look deeper into the structure of nature at its smallest scales. Gravity describes how large things behave: planets, stars, galaxies, and the universe itself. But when scientists study the smallest pieces of reality, atoms, electrons, quarks, they use a different framework entirely: quantum mechanics. And these two descriptions of the universe, both incredibly successful in their own domains, do not fit together. Quantum mechanics tells us that at tiny scales, nature is probabilistic. Particles do not have definite positions or paths. They exist in clouds of possibility, described by wave functions. Events happen with probabilities, not certainties. Reality at this level is fuzzy, jittery, and unpredictable. General relativity, on the other hand, treats space-time as smooth and continuous. Curvature changes gently, like a stretched fabric, but when enormous mass is compressed into extremely small regions, as in black holes or the earliest moments of the universe, these two pictures collide. At the center of a black hole, Einstein's equations predict a singularity, a point where density becomes infinite and spacetime curvature becomes undefined. Physics breaks down. The equations stop making sense. Nature is telling us that our understanding is incomplete. This is not a failure of Einstein's theory. It's a sign of its limits. Just as Newton's gravity worked beautifully, but was later revealed to be an approximation, Einstein's gravity may also be part of a deeper framework still waiting to be discovered. Scientists today are searching for a theory of quantum gravity, a way to describe spacetime itself using quantum principles. This effort has led to ideas like loop quantum gravity, string theory, and other approaches that attempt to reconcile geometry with uncertainty. None of these theories is complete yet. None has been experimentally confirmed, but the search itself is guided by the same principle that led from Newton to Einstein, when two ideas work perfectly but refuse to fit together. Nature is asking a deeper question, and gravity keeps asking it. Gravity is strangely weak compared to other forces. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. Why is gravity so much weaker than electromagnetism? Why does mass curve spacetime while electric charge does something entirely different? We don't know. What we do know is that gravity governs the structure of the universe on the largest scales. Galaxies form because matter follows curved spacetime. Clusters of galaxies orbit one another. The expansion of the universe itself is shaped by gravitational geometry. But even here, new mysteries appear. When astronomers measure how galaxies rotate, they find something unexpected. Stars far from the galactic center move too fast. According to visible matter alone, galaxies should fly apart. But they don't. Something unseen is providing additional gravitational curvature. We call it dark matter, not because we know what it is, but because we see its effects without seeing the thing itself. Dark matter does not emit light. It does not absorb light. It interacts almost entirely through gravity. Its presence is inferred from the way spacetime curves, not from what telescopes can directly observe. Again, gravity is acting as a messenger, revealing something real without showing us what it is. Even more puzzling is dark energy, a mysterious influence causing the expansion of the universe to accelerate. Space itself appears to be stretching faster over time, not slowing down as gravity alone would suggest, but speeding up. This acceleration comes not from matter pulling inward, but from spacetime itself behaving differently on cosmic scales. Gravity, the geometry of spacetime, is not static. It evolves, it responds, it carries energy. When massive objects like black holes collide, they disturb spacetime itself, sending ripples outward at the speed of light. These ripples, gravitational waves, were predicted by Einstein and detected a century later. What reaches Earth is not matter or light, but motion in the fabric of reality itself. Space stretches and compresses by fractions of the width of an atom, and our instruments feel it. This means space-time is not just a passive stage where events happen. It is a dynamic participant in the universe. And that brings us to something subtle but profound. If gravity is geometry, then space-time is not merely a backdrop. It is part of the physical world. It can bend, vibrate, ripple, and evolve. It carries information. It has structure. This raises a deep philosophical question. What is space, really? In everyday experience, space feels empty, a void where things exist. But physics tells us that even empty, space has properties. It can expand, it can curve, it can transmit waves, it can store energy. Empty space is not nothing, and time, too, is not universal. Clocks tick at different rates depending on motion and gravity. Time slows near massive objects. Time slows for fast-moving observers. Past, present, and future are not absolute. Reality is not divided neatly into space and time. They are interwoven. This realization changes how we think about motion itself. In Newton's world, objects move through space over time. In Einstein's world, objects trace paths through space-time. Motion is not just where you go, but how you move through time itself. Your life is a path through space-time. So is the moon's orbit. So is a beam of light from a distant galaxy. Everything that exists traces a line through this four-dimensional geometry. Gravity shapes those lines. And yet, despite all this abstraction, gravity remains deeply connected to everyday experience. When you sit in a chair, the chair is pushing you away from your natural space-time path. When you jump, you briefly escape that push. When you fall, you are not being pulled, you are released. This perspective reverses intuition. Stillness requires force. Motion does not. Standing on the ground means being accelerated. Falling means being free. This is not just poetry, it is precise physics. Understanding gravity this way also reshapes how we teach science. It reminds us that equations are not the goal. Understanding is. The purpose of a theory is not just prediction, but insight, revealing what nature is doing behind the numbers. Newton's equations were not wrong. They were incomplete. Einstein did not discard them. He showed why they work and where they fail. And someday, a deeper theory may do the same for Einstein. That is how science progresses, not by erasing the past, but by embedding it within something larger. At every stage, curiosity drives the process. The refusal to accept unexplained coincidences. The willingness to question assumptions that feel obvious. Why do all objects fall the same way? Why does mass curve space-time? Why does the universe have the structure it does? Each answer opens new questions. And that is not a weakness of science, it is its strength. Gravity, once thought to be a simple pull, turned out to be a window into the nature of reality itself. It connects motion, geometry, time, energy, and the large-scale structure of the cosmos into a single idea. From the fall of an apple to the collision of black holes, the same principle applies. Objects move as space-time allows them to move. Mass shapes spacetime. Spacetime shapes motion. That quiet relationship governs everything we see. And perhaps the most remarkable part is this: the universe does not demand we understand it, but it allows us to. Through careful observation, honest questioning, and mathematical imagination, human beings have uncovered patterns woven into the fabric of existence. Gravity is not a mystery force reaching across emptiness. It is the shape of the stage itself. And when we learn to see that shape, we don't just understand the universe better, we understand our place within it. Not as separate observers standing outside reality, but as participants moving along its curves, moment by moment, carried forward by the geometry of space and time.